today's webinar. So the topic of today's webinar is intact intelligent tropical storm resilient system for coastal cities in a changing climate, which is very interesting and very relevant topic. So next, let me introduce today's speaker. Dr. Yu Dong is a social professor in the Department of Civil and Environmental Engineering at the Hong Kong Polytechnic University, PolyU. His research focuses on risk, resilience, and sustainability-informed assessment, as well as life cycle intelligent maintenance of engineering assets and deterioration hazards and climate change. His research group specializes in data-driven computational modeling, physics-guided deep learning, and digital twin-enabled intelligent maintenance, with applications in civil infrastructure, transportation networks, cyber physical systems, and interdependent infrastructure systems. Dr. Dong serves as associate editor for several leading journals, including the Journal of Structural Engineering, Structures, Journal of Engineering, and as an editorial board member for journals such as Structural Safety and Reliability Engineering and Systems Safety. He has received multiple prestigious awards, including the IASSAR Early Achievement Research Award, the IALCCE Junior Award, and the IABMAS Young Award, and has been recognized as one of the Stanford University's world top 2% scientists. So without further ado, let me stop sharing and give the floor to Dr. Dong.
Thank you, Zai Shang. Thank you for your introduction. I'd also like to thank Dina for your kind invitation. So it's my great honor and pleasure to show the work that we have done at PolyU, at the department and at Civil and Environmental Engineering. Actually, this year our department research team has secured several research projects regarding the resiliency in a changing climate. Because Hong Kong is like coastal city, the local government here is quite emphasize the development for the Hong Kong, under the future climate change. So here in our department and also in my research group, may emphasize how to develop the resilient infrastructure system in a changing climate, like how to doing the resiliency quantification, and also most importantly, how to do the decision making and the future climate change. So this is the reason why in today's presentations, I may emphasize how to basis on the evaluation, basis on the assessment, basis on the risk, resiliency quantification, how we could do the decision making. I think decision making is really important, for the coastal infrastructure in a changing climate. So this is main things that I try to cover in today's presentations. Now give some basic backgrounds why the urban resiliency in a changing climate is quite important. So why Hong Kong is like coastal city, why we want to emphasize urban resiliency by considering the future climate change. As we know that Hong Kong is like a coastal city, each year we almost have the tropical cyclone. Like number 10, actually this is the biggest typhoon scale in Hong Kong, can hit Hong Kong every 4 years. This is for the big typhoon, Mangkhut, happened to Hong Kong at number 10. This is called 115 billion damage. So this is for the total direct loss around 5 billion Hong Kong dollars. Actually, when we considering the indirect loss, that's be much larger than the direct loss. So how to assess the risk, how to do the resiliency quantification, for the Hong Kong and the future climate change, that is really important. Here you can see this is quite a unique phenomenon in Hong Kong in 2024. There is kind of for tropical cyclone in the South China Sea area. This is for the tropical cyclone. The tropical cyclone is like hurricane in the United States, but in Hong Kong we call it tropical cyclone, but the same meaning as the hurricanes. And also another thing that we try to emphasize here is for the compound hazards. It's not only just the tropical cyclone, but it's also the heat wave, some other compound hazard effect on the coastal cities. So when we talk about for the future, I mean, when we try to do the prediction for the future, we have to consider the climate change. Climate change can definitely affect the hazard pattern, I mean, the intensity and the durations. So that means that maybe the currents, like the probability maybe become smaller, but I can say the climate change by the intensity, the duration for the severe like tropical cyclone can significantly increase by considering climate change effect. And also we have to considering the compound hazards on the coastal infrastructures by considering the recovery. Because for the resilience, it's not only the damage, but also the recovery, like after the heat wave before and after the tropical cyclone, that can also cause some kind of mental problems. So this is also acts as one motivation for our research group by considering the future climate change. We have to make sure that whether our coastal infrastructure is ready for the future climate change, because these kind of scenarios like rare and severe hazards can be more common. So this is acts as the motivation for our group. We all know that climate change, climate adaptation, this is definitely a multidisciplinary or interdisciplinary approach. But as engineers, what is like the research challenge? I think the research challenge from the engineers, like how we could doing the performance quantification and the in a life cycle context and the different type of the uncertainties. So this is for the life cycle engineering. In my PhD, I have worked a lot on the life cycle, how to do the life cycle assessment and also the prediction. We know that within service life, the structure have different deterioration, aging effects, and also within service life, they could under different headers like extreme events. Then we do the repair, we should do the maintenance. And also with the evaluation procedures, we have different type of the uncertainties. We have to take the uncertainty into the consideration. And also we have to consider the stochastic process within different, like the climate change with different hazard scenarios. By considering the climate change, maybe the stochastic process can become non-homogeneous Poisson process. So this can become more complicated like a stochastic process. So how to do this kind of evaluation, that is really, really important. So that means that when we try to do the evaluate climate change effects on the coastal infrastructure to develop more resilient infrastructure, first we have doing this kind of quantifications. We are doing this kind of prediction. So it means that we have to quantify the life cycle prediction and the multi-hazards by considering the degradations like chloride induced corrosion, carbonation. So we have different deterioration scenarios. But this is also quite challenging problems because we have to consider different stochastic model. It's not only just PDF, CDF, it's also we have different stochastic process within the hazards occurrence. By considering climate change, the hazard pattern may also be changed. So we have to consider different stochastic process. And then we have to quantify the time-dependent filling probability, not time invariant. We have to quantify the time-dependent filling probability by considering different hazard scenarios. And we can use the Monte Carlo simulation, but this is kind of really time consuming. So this reason why in this kind of evaluation procedures, I mean, we can incorporate this kind of physics-informed AI to develop this kind of high-fidelity time-dependent assessments. So based on this kind of time-dependent reliability analysis, we could predict what is infrastructure performance by considering different hazards and also by considering the climate change effects. So this part is regarding how to evaluate the condition within the service life for our coastal infrastructures within the 75 years, within 100 years, how we could evaluate their time-dependent performance. So this is regarding for the performance assessment and prediction. Once we have this kind of prediction as engineering problem, then we could considering their like performance. We could consider the durability. We could consider durability from material level to the structure level to the system level. And within the design, we have to consider different type of limit states. We have ultimate limit state, we have serviceability limit states, we have the extreme event limit states. For the extreme event limit state, maybe that is more relevant to the resilience. But for other limit states, we have to consider the reliability and the risk. So based on their performance, we can do the evaluation, we can do the prediction, then we could determine their time-dependent performance, and also we could calculate the life cycle cost. So this is regarding for decision-making part. So previously we do this kind of evaluation for the time-dependence, reliability, risk, resiliency. I think the next step is how we make the decision. How to the decision? We have different type of the objective. We want to improve the performance, reduce the risk, improve the reliability, improve the resiliency within life cycle. So this is kind of decision-making process. So it's like optimization problems. Within the optimization problem, we can use different like optimizer to solve these kind of problems. But once we can see during the climate change, once we include different type of uncertainties in this kind of stochastic environment, we could think about how we could use the deep reinforcement learning to solve this kind of problems. So this is kind of within our research group. First, we try to do this kind of long-term predictions by considering the future climate change and considering different type uncertainties for the time-dependent reliability risk quantifications. So based on predictions, then we more emphasize on how we could do this kind of adaptations by considering the climate change. But for the climate change adaptations, not only optimization important, but the robust decision-making that is also quite important. Once after that, I'd like to take the wind engineering as the example. So this is our work that with my previous postdoc, Jiayao Wang. Now she's a postdoc in Notre Dame. For instance, first we have doing this kind of large-scale climate change modeling. We have different like scenarios, SSP, RCP, and also we have doing this kind of downscales from large scale to the regional scales. Then we could determine what is the climate change effect on our regional scenarios. Then we have to evaluate what is like for the climate change effect on the wind parameters, like on the wind speeds, on the wind directions, and we have to consider different wind profile without climate change scenarios. This is kind of multidisciplinary approach. We have to work with climatologists. They give this kind of climate modeling, and also we are doing the downscaling to evaluate what is the future climate change on the wind profile. That's once we have this kind of loading, and we have to evaluate what is the infrastructure performance and the scenarios without climate change. We have to using the fragility model. We have to develop the feeling probability and the different climate change scenarios. So out of that, we could quantify the fragility. We could identify the vulnerability model. And also we have doing this kind of quantification for this kind of risk. I mean, we have to consider different type of the consequences. I mean, we have the direct consequences, and also we have the indirect consequences. Besides that, and also we try to incorporate the sustainability and the performance indicators. So this is what I mentioned before. We could include different type of the indicator at the decision making, at the evaluation procedures, like from the reliability, risk, resiliency, and also the sustainability. And then we could using different like optimization algorithm to determine which type action we could use to enhance the resiliency for our coastal infrastructures. Again, here, this is really quite interdisciplinary research. We have the collaborations with people from the climate science, but here we may emphasize how to do the infrastructure performance under different climate change scenarios. Then based on this kind of prediction, the future we will doing this kind of adaptations by considering the climate change scenarios. Overall, this is our group mission at PolyU. We really try to enhance the urban resilience, like for the urban coastal infrastructures. And then we try to develop different adaptation strategies and the compound hazard by considering the climate change scenarios. That means we have to work on the coastal bridge, coastal building, considering the dependency and the interdependency among different infrastructure systems. So based on our evaluation prediction, then we could think about how we could do the adaptation for our coastal infrastructures. And also, this is like for the general approach. We try to solve this kind of big problems. We have developed this kind of multidisciplinary group. We have people working on the climate change modeling. Then we will focus on the coastal infrastructure. We do the downscaling to see what is the flooding, what winds on coastal infrastructure. This means that we emphasize on this kind of extreme hazards. Then we evaluate what is the extreme hazards on the coastal community, what is damage. We have the direct consequences, we have indirect consequences. Besides that, we want to emphasize on the recovery. We all know that the resilience emphasize on the recovery, emphasize on the functionality. So we work on the like social scientists to evaluate what is the climate change, what is the like extreme hazards on the human, on the social economy perspective. The last but not least, I think the policy, the decision making is also important. By using the decision making, by using policy, we can make sure that our research outcome can benefit our society. Again, we have formed this kind of interdisciplinary research group at PolyU, at our faculty. For my part, mainly emphasize how to do the risk resilience quantification, how to evaluate their performance, how doing the prediction for the coastal infrastructure by considering the climate change effect, by considering different type uncertainty, by considering the stochastic process. And then we try to make the decision making regarding the retrofit, regarding the adaptation for the coastal infrastructures. I think I will go, actually I divided my presentation into two parts. The first part, I would like to talk about more on this kind of evaluations, on this kind of assessment. This assessment that because once we're doing this kind of performance evaluation, we have to considering different type of uncertainties. We have uncertainty from the structure deterioration. We have uncertainty from loading, the earthquake, hurricanes, they are stochastic process. So we try to develop the surrogate models and also for this kind of uncertainty quantifications. And also within this kind of time-dependent reliability analysis, we try to think about how we could use AI to solve this kind of problem for this kind of uncertainty quantifications. So based on this kind of uncertainty quantifications, then we could evaluate what is time-dependent reliability, what is their performance under different like loading scenarios. So this is like performance evaluation part. I'm sure that we are all quite familiar with this kind of surrogate model for this kind of uncertainty quantifications. I mean, we have maybe for this kind we have large simulation, high fidelity finite elements model. Once we run this kind of model, we have different inputs from the structure parameter, from the loading. We could have different type of the observed data. So this red point is of the data. Then we could develop different type of the surrogate model, like hurricane model, PCE. We could use in different type of surrogate model. But for this kind of time-dependent reliability, we may emphasize on this kind of feeling domain. We more emphasize on the feeling domain. So this reason we could do this kind of uncertain quantifications on this kind of feeling domain. We could do some optimization within this kind of uncertainty quantification parts. As one of the use method is for this adaptive learning or the adaptive correction models, and so this is kind of a benchmark model for this kind of uncertainty quantifications. I think we are quite familiar. First, we have to determine the DOE design of experiments. We have to identify this kind of candidate pools. Then we could develop this kind of correcting model. But within this process, we could do different type of the modifications, improvements to enhance the computational efficiency and also to improve the accuracy. So it means that we can change the learning functions. We could use different learning functions instead of learning, and also we could change the stop criterion. So in this way, try to make this kind of uncertainty quantification like more efficient. I mean that we do not have to using 10 points. Maybe we can using like 5 or 3 points. We could achieve good results. So within my group, I have within my research group, because I have joined Poly for around 10 years, we have done a lot for this kind of time-dependent reliability analysis. Basically, for this kind of time-dependent reliability analysis, we could base it on sampling-based methods like Monte Carlo simulation, important sampling, subset simulations. This is high accuracy, but if we involve this kind of high fidelity model, so this is quite time consuming, then we could develop the surrogate model. So this is also quite one options. Besides that, we could also using the probability density informed like the point evolution, kernel density estimations. But this approach have this kind of curse of the dimensionability and also cannot well apply to this kind of stochastic problems. So this is the main reason in our research group, we have done lots for this kind of uncertainty quantification. We try to do this kind of time-dependent reliability analysis. So we have to consider different type of the stochastic process. We try to evaluate what is time-dependent reliability. So here we try to integrate the point evolution theory with the physics-informed AI techniques to solve different type problems. But here we not try to see that AI can solve all these kind of problem, all the problem we can use AI to solve problem. Only for the specific problem, we think we can use the AIs like PRNN to solve the specific problems. So this is our approach. Generally, our overall goal is to make sure that the assessment, the prediction procedure, because the resilience is more emphasize the extreme events. The extreme event is kind of stochastic process. We try to evaluate under this kind of stochastic process, what is the infrastructure failure probability. So given this kind of failure probability, we could quantify the risk, and also we could do follow up for the resiliency quantification by considering the functionality, by considering the recovery strategies. Here for our proposed approach, we generally can achieve the high accuracy, and also we could consider the stochastic process because the hazards definitely is kind of stochastic process, and also we could incorporate the physical information within the time-dependent prediction procedure. First, I think I would like to represent this kind of three events, three algorithms that we have developed in our research group. I think you can scan the QR code. You will be a link to our relevant study. The first study we try to evaluate on the efficient real event estimations. I think this is really, really important because when we consider the climate change, we have to consider the long tail behaviors. So it means that we have to emphasize on this kind of low probability, high consequence events. So this is the main reason why we propose methods for this kind of efficient real event estimations for the smaller failure probability like quantifications. The second method that we try to incorporate the physical information to solve like time-dependent reliability problems. And last but not least, we try to evaluate considering a different type of stochastic process, how to doing this kind of basis on the long short-term memory, basis on this kind of point evolution, kernel density estimations. We try to evaluate under different stochastic process, how we could quantify the time-dependent reliability analysis. So here, I think for more detailed information, you can find in this kind of publication, but I will go briefly for our different type of the studies. First is like we try to quantify the smaller failure probability. So this definition for the smaller failure probabilities. It means that the failure probability is like smaller than 10 power minus 4. But here we do have our kind of contributions. So this is our contribution. First, we're using this kind of point evolution kernel density functions. So by using this kernel density estimations, we could perform the probability density functions. Another contribution here, we're using this kind of like the single loop. So to represent for this kind of two loop, then we could develop the CDF, so the first failure probabilities. So this is general computational problems. So this is on this kind of problem we could solve the Phyllian probability for this kind of smaller Phyllian probability events. And you can see here, this is how we propose for this kind of one single loop ideas. So by using this kind of one simple loop idea, if we use this kind of traditional double loop, we have to, at each time step tk, we are doing this kind of analysis. By using this kind of one single loop ideas, we only have to compute the TF. The TF is the first Phyllian time. So this is, we could significantly improve the computational efficiency. Another thing that I would like to emphasize here is for the tail. Because we know that tail is also really important by considering the climate change, because the climate change will have more severe events. So it does mean that we have to quantify what the tail behaviors. So this may reason why we're using the subset simulation to refine the tail region. Then we could have more accurate estimation for the Phyllian probabilities. And also we have to demonstrate the validation of our proposed methods by using different type of the structure system and the different loading. So this is for the simple cases. And also we evaluate for some other more complicated cases. I mean, you can find in the paper. The second one is that we also try to evaluate the physics informed neural network for this kind of time-dependent reliability analysis. So here we really emphasize on the time-dependent reliability analysis. So we try to integrate the physical law within the pure data-driven approach. So that means that when we try to establish the loss functions, we try to develop different type of the loss functions. We have the boundary conditions, we have the inner points, and also we incorporate the physical informed loss. The physical informed loss means that we try to refine this kind of PDF, and by the constraints mean using this kind of generalized density evolution equations. So we have this kind of physical informed loss. Then within the total loss function, we try to incorporate the that loss and the physical informed loss. This is how we develop this kind of loss function. By using this kind of loss function, we could predict what the time-dependent reliability analysis under different loading scenarios. But here I will not go into detail. So this is how we develop this kind of loss functions. We have boundary, we have initial condition, we have the data, and also we have the physical equations. And also we compare our results without physical information. Basically, we can use the lat data set. We could achieve high the accuracy. Meaning that we can only use the 3% of data volume, then we could significantly improve this kind of computational efficiency. At the same time, we want to maintain the accuracy. Again, we really try to demonstrate our approach in different examples. As you can see here, we have different type of the cases, but we do found that our algorithm can solve this kind of problem. And also, I think the domain knowledge is really, really important. Everyone talk about for the AI can solve really many problems. But if we want to solve the AI for the specific problem, we have to incorporate the domain knowledge. So this main reason we have to incorporate the PRNN within the performance assessment procedures. The last but not least, this is also our recent paper. We try to considering the stochastic procedure inputs. As I mentioned before, we consider the resilience. Resiliency is emphasized on the extreme events. Because the extreme events, most extreme events, they follow certain type of the stochastic process, Poisson process, non-homogeneous Poisson process. We have different type of process. So within the evaluation, within the time-dependent evaluation process, we have to take in this kind of stochastic process and consider regions. But the traditional method, they have this kind of curves of the dense, dimensional problems. So this may reason why we have to decouple the stochastic process from this kind of random variable. So this is general computational pipeline as shown here. We also have to train this kind of long short-term memory for different circuits, and also we could use a different sampling method, Latin hypercube sampling or some other like subsets or importance sampling. Then we could identify the initial PDF by the point evolution density, curtain density estimations, and also we try to incorporate the physical information within the loss function. Then we could compute the failure probabilities. Again, this approach is really can solve the problem when we have different type of the stochastic process. We have to the long short-term memory, and we could train this kind of model. And also we have using the PRN, as mentioned before, when we try to incorporate the physical physical law. This is really important when we try to develop this kind of loss functions. So this is kind of core innovation as shown here. For this kind of core innovation, we really try to do this kind of decoupling because we have different type of stochastic process. We try to using this kind of low dimension problems, and also we use long short-term memory to handle this temporary density. Then we could achieve this kind of computational efficiency. Again, we do kind of validation for our approach by using different benchmark examples. I mean, the benchmark example is important. We compare our proposed algorithm with the benchmark and existing method to see what is the efficiency for our proposed methods. So beside the time-dependent reliability analysis, I mean, before we try to develop this kind of mathematical foundation for time-dependent reliability analysis, that means that based on this kind of algorithm, we could determine the vulnerability. We can determine the failure probability. I mean that giving different headers, giving different stochastic process, we could identify what is failure probability, what is the vulnerability for our coastal infrastructures. On that, and also we try to quantify the risk. The risk means that the probability times the consequences. We could identify the risk, and also we have direct consequences, we have indirect consequences, and also we try to incorporate the sustainability. I mean that not only the economic but also the social economy aspects with the evaluation procedures. Actually, all these kind of toolbox is ready. If you have interest, you can send us the email. We are really happy to share this kind of code with our colleagues. And also, we do have different type of the real world applications for the offshore wind turbine, for the coastal infrastructures, like for the bridge, buildings, offshore wind turbine. We try to evaluate what the time dependence reliability, what's the vulnerability for the coastal infrastructure under different hazard scenarios. Again, this is for the mathematical foundation for the time-dependent reliability analysis. Once we could compute the time-dependent reliability, and we could also identify the consequences, like the direct, indirect. We could do the risk quantifications, and also we could do the risk management by using different type of decision-making tools. So this is like for different type applications, and also this is our current work. We really try to focus on this kind of multiphasic informed transformer. So here we emphasize on the wind turbine. We try to evaluate what is the stochastic process for the wind turbine under different loading scenarios. So this is current work that's done by my previously two PhD students. I mean, we have to using the physical knowledge into the transformer model, and also we have to by integrate the structure parameters and into inputs, but also we have to consider some other constraints, like the dynamic resonance and the control. So this is the reason how we could incorporate the physical information to train our model. Then we could evaluate under this kind of multi-physics scenario what the failure probability for different coastal infrastructures. Besides that, and also we have one PhD student that he worked on the power system. For the power system, means that we have to consider the extreme winds, like for the downburst, tornado, tropical cyclone, and also we have to consider different type of the risk category for the power system. We have to consider doing the collapse. We have to consider doing the flashover. I mean, because they are defined for different functionality. I mean, because for the resilience, we have to define what is the functionality. So given this kind of failure mode for the single tower, and also at the network level, right now we are doing the cascading failure. So this is, but now we do not have the really nice result showing here. Hopefully in the future, we have some nice result to see what the cascading failure for the power system under this kind of tropic cyclone. And also we considering the dependency and interdependency for the power system and also for building some other infrastructure system. We try to quantify at the system level how we could quantify the resiliency. So based on this kind of evaluation, then we could do the adaptation. I mean, the decision making, in my point of view, I think is really, really important based on the evaluation, based on the predictions. Once I have mentioned before, given the reliability, given the vulnerability models, and we could easily quantify the risk. I mean, we could quantify the direct consequences, indirect consequences, because we have different type of the consequences. I mean, the probability times the consequences, we could identify the risk. But within the risk quantification, we also have to consider the hazard scenarios, because they have different type of the stochastic process. Beside the risk, we all know that nowadays the resiliency and also the sustainability is also quite important. In my opinion, I think the resiliency is also quite interdisciplinary approach. It's not only in the engineering perspective. When we try to quantify the resiliency, we have to first give it the vulnerability. Then we have to considering the recovery scenarios. We have to considering like what is the social economy perspective, and also we have to evaluate what is the health effect on the human beings. The humans like the who use the infrastructures, and also we have to consider dependency and interdependency, because that is quite relevant to the recoveries. Like we have to consider the dependency and the interdependency effects on the resilience quantification on the recovery stage. And also in our research, we considering the sustainability. Sustainability means that we not only care about for ourselves, but also we care about for our future generations. We have to consider the social aspect, economic aspects, and also this kind of environmental perspective, like considering the carbon emission, considering energy consumption. That is related to the recovery regarding for the adaptations. So this is based on the time-dependent reliability. We could consider different performance indicators. I think this is kind of from one performance indicators to different performance indicators. The different performance indicators do have a different type of relationship, but also they have different things that they emphasize on different perspective. Like for the resiliency, maybe this is more emphasize at large scale, emphasize at the functionality, emphasize on the recovery. Sustainability maybe is like more big topic, but within engineering, we have to think about within the performance assessment, within the prediction. We have to have a metric there to quantify the sustainability, like carbon, energy. I think this is also really, really important when we try to make the adaptation for the infrastructure and the climate change scenarios. So here, this is for the risk resiliency platform, because once we have this kind of time dependency reliability assessment toolbox in our research group, and also we try to develop our own algorithm for the resiliency and risk quantifications. I mean here, from physical damage to the downtime, because downtime is quite relevant to the indirect consequences. And also because Hong Kong is kind of financial center, the financial loss for economic perspective, we think that is really also quite important. Like we try to talk to the insurance and reinsurance company, how to do this kind of insurance research. And also from the loss of the carbon emissions, that is more emphasized on the sustainability perspective. Because of the climate change, like from the stationary to the time variant methods in changing climates. So this is also quite relevant, because the climate change will change the pattern for the hazard occurrence, like maybe from the stationary to the time variant methods. And also we have to emphasize on the recovery and mitigation, not only the mitigation, but also the adaptation. That is also quite important for the risk and resiliency quantifications. And also, once we have these kind of things, so this is our recently project. Our recently project, because before we may emphasize on this kind of tropical cyclone, now we have a new project that's work on the compound header. Compound headers mean that we try to evaluate on the cascading effect. Cascading effect means that we mentioned before, we try to evaluate the single failure, which is called the whole system failure. We try to doing this kind of network modeling because we have developed different types of vulnerability model for different infrastructure systems within the network. And then we have to evaluate what is the smaller failure and trigger the whole system failure. And also within this procedure, we try to consider the compound headers. I mean, like before and after the tropical cyclone, maybe there's a large heat wave. The heat wave kind of will affect the workers' workabilities. That will kind of affect the recovery stage. We know that the recovery is relevant to the resilience because we think this is also quite relevant. Again, so this is for our multi-layers like resiliency and recovery model. First, we emphasize on the infrastructure, but again, I think for the resilience, we have to extend from single building cluster to the system level. And also we have to consider the social functionality, and then we could try to develop the community resiliency by considering like the deep uncertainty, by considering the dependency and the interdependency. Then at the system level, at the community level, how we could enhance the resiliency. I think this is also the current work because Hong Kong is like density city, everything is highly connected. We are lucky that we have the local government support. We have kind of data to do validation for some parts of our study. So this is we really get strong support for the Hong Kong local government. They emphasize on climate change, emphasize on climate adaptations. So this is reason why we have formed like a research group, interdisciplinary research group to tackle this kind of challenge problems. Also, once basis on this kind of evaluation, I mentioned from my perspective, I think the decision making is become more and more important. We're doing this kind of evaluation, we're doing this kind of prediction. But I think the final goal is that to make sure that our final products, our final outcome, the decision maker, maybe the government, like the insurance and insurance companies, they can use our outcome to do some kind of decision making. So this is the second part I try to talk about for the decision making. I still have time. For the decision making part, again, this decision making is from the engineering perspective. We have to develop this kind of mathematical foundation. I think math is really important. We have to rely on the math to make sure that we could explain things why the physical model that's important. I think math is also quite important. Then we have to develop this kind of computational framework. The computational framework means that we should know what is infrastructure or the infrastructure system performance, their deterioration, their performance under different hazards, and what is their vulnerability, what is the redundancy, what is the recovery, what is the resiliency, and also we have to take the cost into the consideration, like the repair, retrofit, recovery. So this is kind of different type of conflicting objective. So then we have to make the decision. That means that we have to use a different type algorithm to solve this kind of optimization problem. Maybe we want to reduce the cost. We want to improve the performance. So this is kind of decision making problems. Within this kind of decision making problems, I would like to give the simple examples that we use in the surrogate basic decision making. So this is the reason why at the very beginning I spent a lot of time to introduce for the surrogate model for the time-dependent reliability analysis. I think this is important because when we try to make a decision making, we have to considering the future scenarios. For the future loading, that high probability, future climate change, deep uncertainty. So we have to develop this kind of surrogate models. I mean, we have to first have this kind of performance assessments, and also we have to develop this kind of surrogate-based optimization that we could do in the decision-making part. I mean, first we have to develop. First we have to develop this performance-based assessments. We have doing this kind of hazards assessments, considering the climate change. We have doing the damage, different damage states. We have to identify the consequences. Then we could develop the surrogate model-based optimization. And also we could do this kind of sampling. Then we can use different algorithms. We can use GA, we can use some other algorithm to solve these kind of problems. But with the decision-making procedure, the attitude, the risk perception, that is also really, really important. We have to determine the attitude for decision maker, risk aversion, risk taking, risk neutral, because that will affect the decision making result. So I mean, this is also quite important. You can see here, this is kind of general approach. We try to do this kind of efficient optimization for the community. I mean that we want to, as the community, for the building portfolio, by considering the future climate change, by considering the future flooding, like also maybe for the earthquake, how we could do in the retrofit. I mean, we have to study for different data set for the individual buildings. We do the performance-based assessments, and also we have to consider different return period, and also we have to consider different type of the consequences. Then we have to develop different type of optimization criteria. We want to reduce the cost. We want to improve their performance. Then we can use different optimizer to solve these kind of problems. I think also within the performance assessment procedures, we can use in the expected annual consequences. But I mentioned before, the decision maker attitude, that is also quite important. Also, this main reason here, we introduce the utility theory. By using the utility theory, we can consider the attitude for different decision maker. I mean, they can risk neutral, risk taking, risk averse. I mean, given different attitude, the final result can be different. So in this study, we try to evaluate what is the risk attitude on the final optimum solution. Actually, here we have like certain apparent optimum solutions, and also within the optimization procedures, we could identify the design variables. We can design the objective, and also we can design the risk attitudes. As you can see here, we could considering different objective. We want to reduce the cost, reduce the fatality, reduce the repair cost, reduce the repair time, and also reduce the emission and embodied energy. But at the same time, we want to enhance the resiliency. So this is kind of multi-object optimization. We can use the utility theory by considering different risk attitudes with the decision-making procedures. So this work is also done by my previous PhD students, Ali, and he's from Pakistan. And also, we compare our algorithm with like the basic decision making, and also we compare the surrogate model. I mean, with the decision making, and also we want to improve this kind of decision making efficiency by using different optimization algorithm. But here, this is one type of decision making problems. I mean that we have to considering the design variable, we have to determine the constraint, and also we can use different optimizer to solve these kind of problems. Right now, when we try to make a decision under this kind of stochastic environments, we can try to think about for the deep reinforcement learning. Deep reinforcement learning, this is kind of for decision making under the stochastic environments. I mean, we have to like the interaction, the agents, the interaction with the environments. We have to identify a different type of action, and also we have to identify different type of the rewards. All these kinds of like mathematical foundation we form in the POMDP. I mean, we form in this kind of partially observed Markov chain decision making process. So Markov chain decision making process. So this is a commonly used method for decision making. But within the decision-making procedure, we can have the data from the health monitoring, from damage data, assuming that we can input some kind of information to solve this kind of decision-making under this kind of stochastic process. Here, we can use different algorithms like actor critic, like A3C. So we have different type of algorithm using the deep reinforcement learning for the decision making. We have applied this kind of approach to the different infrastructures. I mean, we have to consider the interaction with the environment, because that means that under the detailed region under the climate change, under the hurricane, what is their performance? Then we have to identify the maintenance actions. We can do the inspection, we can do the maintenance, and also we have to identify their current state. So given different current states, their failing probability is different. And also we have to identify the rewards. We want to reduce the fee, and we want to reduce the risk. And because all these kind of things is probabilistic, we use this kind of partially observed Markov chain decision-making process to determine the optimal policy under this kind of stochastic problem. Then we could.
Hi, you don't, Tommy.
Yes.
Would you be able to use the pointer when describing your slides? Because some of our listeners, yes, that would be very helpful. Thank you.
Because there's something wrong with my mind. I try to use that. Sometimes it's not working at this computer.
Yes. Thank you. So, thank you very much.
So this is how we could identify.
People can follow better.
Can identify different rewards, and also we could identify this kind of maintenance strategy. But here again, we really try to promote this method for the local governments. Like in Hong Kong, we doing the maintenance, like for the Hong Kong to have Malacca Bridge. Again, I think maybe sometimes if you want to use this algorithm for the like partially observed Markov chain decision-making process and the deep reinforcement learning. Sometimes this is kind of cannot directly solve the problem, but by using this method, we can give in different type of the policy by considering different objective. And also, this is like another work that is by my first PhD student. Right now, she's the assistant professor in the Hong Kong Metropolitan University. For this kind of study, Dr. Yaohan Li, she tried to emphasize on the decision making and the deep uncertainty. We mentioned before the previously for decision making, they emphasize on optimal solution. But considering the climate change is deep uncertainties. We have different SSB scenarios. So there's a deep uncertainty. So this mirror why in her research, we try to not doing the only the optimization, but also how to identify the robust decision-making, robustness for the adaptation. I think that is also quite important. We know that this is basic definition for the deep uncertainties. I mean, for deep uncertainty that we cannot using the PDF, CDF to identify the distribution, and we cannot fully understand this kind of uncertainties. So this reason why we have to treat this kind of epistemic uncertainties, and also how we could determine not only the optimum, but also the robust climate adaptations. Again, this is also quite interdisciplinary because we have to identify the possible climate change scenarios. We have SSP, different scenarios. There we have to identify which scenarios maybe work for our areas because different infrastructure, they are located in different areas. And also we have to talk to the people working on climate change, talk to the local designers, then we can propose some solutions, then considering the uncertainty, considering the real design, retrofit scenarios. And also we have to considering the epistemic uncertainties, how to make sure that our final adaptation actions can really solve the real world problems. And also this kind of Yaohan has done a lot of work like how to do this kind of deep uncertainties under the future climate change. As you can see here, we have the cascading for these kind of uncertainties. I mean, from large scale to the low scale, how we could do this kind of downscale, how we could do this kind of adaptation actions. I think within this kind of procedure, the dynamic decision making, that is really, really important by considering the future climate change, because this is kind of deep uncertainties within the decision making procedures. I think here Yaohan proposed this kind of degree of belief in different model and epistemic uncertainties. Then within the decision making, we try to identify not only the optimal, but also the robust adaptation actions. So this is also kind of collaborative research project that I work with Yaohan for a while, and also Yaohan has some other collaborators, how we could promote the robust like adaptation considering the epistemic uncertainty. Here we refer to the deep uncertainties. I mean, we cannot easily use the PDF or this kind of like low-bound, upbound to identify this type uncertainties. I think this is also quite important, how to make the robust decision making by considering the future climate change. Also, this is some our work, like we will try to doing this kind of resiliency quantifications for this kind of infrastructure system. How we could doing this kind of resiliency quantifications, like before the event, during the after the event, within the restoration stage, we have to consider in different stage. Maybe at a different stage, our emphasize things is different. Maybe within the pre-event, we have to identify the reliability, the failure probabilities. Within the operation, we have to considering the resourcefulness. We have to consider impeding factors. We have to consider the event process, the recovery process. Also, of the post-event, we also have to consider the recovery strategies. Besides that, this is only the engineering perspective. And also, we have to consider the social economic perspective for the resiliency quantifications. I mean, Zai Shang, I mean, he had done a lot of work on this kind of human-centered resiliency. I would like to happy to have some collaborations. Again, I think resilience is really kind of interdisciplinary topic. For the engineering, maybe we more emphasize on the vulnerability model, time-dependent reliability assessments. But considering the decision making, we have to incorporate researchers from other disciplinary, other research area, like for the how to do the social aspect, economic aspects. We could identify different consequences. So based on this kind of evaluation, risk or resiliency, then we could make the robust and optimum decisions. And here we really emphasize on how to do this kind of resiliency enhancement for the complex infrastructure system. Like as shown here, this is like between Hong Kong for the prevention against the certain disruptions. Again, Hong Kong is kind of tiny city, everything is highly interconnected. A single failure can cause the whole system failure. So we try to evaluate this kind of cascading failure effect, how we could prevent for this kind of uncertainty disruption. And also we're using this kind of operation for the system resiliency by considering multi-stage. Multi-stage disruption means that once we have this kind of new information, how we could quantify the value of the information, then we could make the sequence decision makings. Others more emphasize on the resiliency enhancements and this kind of cyber physical risk and the different not only the natural hazard but also this kind of man-made for the cyber attack, how to enhance the whole system resiliency by considering different scenarios. Again, I think for the resilience assessments and resilience enhancements, first we have doing this kind of evaluation to identify the reliability. Then we could doing the performance assessments in terms of the risk, reliability, resiliency, sustainability, and also we have to consider in the future climate change, deep uncertainty. Then we could identify what are the optimum and also what are the robust options for our coastal infrastructures. So there are kind of key takeaways. I will not repeat here, but generally I think time-dependent reliability analysis is important. How to do the life cycle assessment is important because my PhD work on the life cycle. I mean, life cycle evaluation, prediction, how to assess the time-dependent reliability. I think this is the foundation for the risk resiliency quantifications. But once we incorporate the climate change, we have to consider the large scale, spatial and temporal large scale. We have to consider the cascading failure. We have to consider tail behaviors. So this is the main reason why in our group we emphasize on this kind of low probability, high consequence events. Last but not least, we think the climate adaptations. This is really multidisciplinary or interdisciplinary research topic. It's not me that's done all this kind of work. We have kind of project from the Hong Kong governments. We do have this kind of interdisciplinary team to solve these kind of problems. But as engineers, I think we have to make sure that our research outcome can really benefit the like the society can benefit the governments. Also, this is the main reason why we have to think about for decision making. Regarding the decision making part, we have to identify optimal solutions. At the same time, because of climate change, again, deep uncertainty, we have to incorporate the robustness, like the dynamic decision making. I think that is really, really important. Again, I think this is really kind of interdisciplinary approach. For me, my research group, we love to do this kind of multidisciplinary topic. We love to talk to people from other disciplines. So we have kind of monthly meeting with people from the computer science, from the like climatologist, from like decision making parts. And also we do look forward to the collaboration with Dina's research group. I really appreciate that Dina give this kind of opportunities. Also, I would like to thank Zaishang for the kind invitation. So that is all my presentations. I would like to have to take any question from the audience. Thank you, Zaishang.
Thank you, Dr. Dong, for this very impressive and, of course, very informative presentation. So yes, I found that there have been a few questions in the Q&A box. So the first few questions are raised by Akhtaruzaman Hassan. So we can allow you to speak. Would you like to introduce yourself and introduce your, also ask your questions? I've seen a few questions from you. Akhtaruzaman, would you like to speak? Hello? Okay, maybe let me repeat the question. So Bangladesh is a climate vulnerable country. We can introduce high-speed nano satellite for forecasting. And yes, please. I saw you. Yes, please.
Thank you. Actually, I've already mentioned my questions over there.
Yes.
Would you like to introduce yourself, and maybe you can provide more details on your questions?
Okay, thank you very much. Thank you. I'm Hassan. I'm right now pursuing my PhD in Monash University, Malaysia, as well as I'm an executive engineer of Government of Bangladesh in local government engineering department. Thank you.
Okay, thank you, Hassan. So Hassan's question is, maybe you can start from the third comment. LCA will vary from a climate scenario to scenario, and there are countries, if FCA is taken all instant, then costs become huge. Do you have any suggestion on it?
Yes, because actually my PhD, for my PhD study, my PhD is done at Lehigh with Professor Dan Franco. We have worked a lot on the life cycle, LCA life cycle assessments. As you mentioned, like when we're doing this kind of consequence computation, we have to identify the direct consequences and indirect consequences. If we incorporate all these kind of indirect consequences within the assessment procedure, the LCA will be huge. So this is the reason why when we make the decision making process, when we try to quantify the LCA, we have to think about who we are talking to. We are talking to a government, or we are talking to the owner of the buildings. So given different decision makers, I think the LCA computation, the calculation is different. It means that given the specific engineering problems, we have to identify how to quantify the LCA. So given different decision maker, and also for the attitudes, this is also quite important. So we have to consider different scenarios within the LCA quantification procedures. But for the LCA, we have basic standardized procedures. Like we have to consider the initial cost, construction cost, operation maintenance cost, and the demolish costs. So this is within this kind of procedures. Then we have to think about which is more critical for the decision maker. Then we can think about which type of consequences we can evaluate on the LCA assessment procedures. Hopefully I answer your question.
Yes, I got it. Thanks.
Thank you.
Okay. Thanks. And another question from Hassan is, if you can your model replicate elsewhere?
Okay.
Can your model replicate elsewhere? I mean, I think if your
Yeah,
model
sure.
can be,
So I think I think if you send our like email, we are happy to share our code with you guys. And we do this kind of value. I'm really open to share all this kind of, because you see here we have different type of the time dependent reliability toolbox. We are really happy in the future we can share this kind of like string here. We have different type of the algorithm to do this kind of time dependent reliability. We are happy to share the code with you guys. You can send us the email. I think I put my email address here.
yes, good. Thank you. And a question from an anonymous attendee is, what type of model are you using to incorporate social aspect into infrastructure vulnerabilities?
These really good questions. For me, that I think the social vulnerability index is really, really important. Today, I talk a lot for this kind of engineer vulnerability models. Engineer vulnerability model means that we can see the capacity for the structure, the load from outside, then we develop the performance function, limit state function, we identify the reliability index. But the social vulnerability, that's really, really important. It's like the people who use these kind of buildings. So this may reason why in Hong Kong we try to identify the social vulnerability index for different type of the area in the Hong Kong, because the income is different, their language like level is different. For that part, we collaborate with research and policy from the social departments. Sometimes they give all this kind of like basic information. When we try to quantify this kind of like engineer vulnerabilities, we introduce certain factors like for the social vulnerability index. So here that we try to do in our research group, we try to combine like engineer vulnerability and social vulnerability within this kind of infrastructure performance evaluation procedures. So that means that we have two types of buildings. I mean, maybe their language level is different. When something like emergency event happens, maybe people from this kind of building, they cannot read the news because they do not have the their English level is not that high. So that also will affect the people who live in these kind of buildings. So that means that giving the same physical damage, the social perspective can also cause different consequences. So in our like vulnerability models, we try to incorporate the social perspective. But for that part, we really have to work with people from the social departments because they have their standardized methods how to identify the social vulnerability index. We just using the well-established social vulnerability model and incorporate within our engineer vulnerability models. We are working on that, and also we think, for me, I think that is really, really important because it's humans who use these kind of infrastructures. I mean, the human is really important. The social economy aspects, I think, is really important for the infrastructure vulnerability assessment.
Okay, thank you. And next question is from Abbas. Abbas, would you like to introduce yourself? There were your questions.
Yes, hello. Can you hear me?
Yes.
Yeah,
My name is Abbas. I'm a PhD student in University of Geneva, Italy. And first, thank you for very dense presentation, lots of ideas. Could you kindly explain a bit more how you did this multi-objective optimization when you have all of these uncertainties? Because each of the decision variables will have their own distribution. And then when you want to decide which one goes on the Pareto front, how you decide, how you compare the solutions. And I mean, because we need this, then we will move to calculate the how can I say the expected utility. I mean,
yes.
Before calculation, that we need to compare these solutions. This one, this was first question, and the second one is in slide 36 and 37. You mentioned that we didn't want just the optimal solution. We wanted the robust. If you kindly elaborate what was the definition of robust? Because somehow it passes through the optimal solution, yeah. And then how you define that, how do you distinguish that, okay, this one is the robust one? And thank you.
Yeah, thank you for your questions. First, regarding your first questions, like how to considering the uncertainties and also how to considering the multi-objective optimizations. I think that you work on the optimization problems within the multi-objective optimizations. I mean, we have different strategy to solve this kind of problems. One way that we can combine this kind of multi-objective into one objective. I mean, we could assign different type of the weighting factors, and also we could transfer different consequences into the uniform unit. Then we could transfer from multi-object to the single objective. So this is definitely one way. But not with that, as you mentioned, we can using this kind of Pareto optimum solutions. We can considering all these kind of scenarios. We do this kind of optimization for the multi-objective. But again, this is the decision-making problems. The decision-making problems, we have to identify what is the attitude for the decision maker. And for the same problem, if you talk to the like owner of this kind of building, if you talk to the insurance industry, if you talk to the government, their care about things are different. Maybe for this kind of how owner they care about for this kind of retrofit cost. I mean, maybe for the government, they consider the carbon, they consider for this kind of energy. I do think we need kind of questionnaire to identify which objective is more important. Then we can assign different types of weighting to different objective. And also we can use the utility theory to identify their attitudes. So this is also can based on the questionnaire. If you know the utility theories, we have to identify the questionnaire that we could identify the utility functions. So with the utility functions, we could identify their attitudes. So this is how we can solve this kind of multi-object decision making by considering the attitudes, by considering the preferences, the risk perceptions for different decision makers. As you mentioned, like we also have to consider the uncertainties. Like for the earthquake, the one possible solution we can consider all the earthquake scenarios. We can by using the hazard curve, we do this kind of integrations. Then we could identify the mean value, the standard deviations. But for the common, maybe for the normal hazards, we can use the mean value to do the optimization. But once we consider the climate change, we also have to consider the tail behaviors. The tail behavior means that is for this kind of low probability, high consequence events. Then we can use the value at the risk. So this is also if I remember, this is also the term that used in the insurance and reinsurance. So given the distribution, we could identify what is value at the risk. So that means that with the decision-making process, we can not only consider the mean, but also the standard deviation. I mean the third moment or the fourth moment skewness. We have to consider different distribution with the decision-making procedures. I think this is also, again, this is based on decision maker, which kind of criteria they want to consider, the mean, the standard deviation, third or second or fourth moments. Then we can consider different perspective with their decision-making procedures. So this is by using this kind of approach, we could identify the optimum solutions. I mean, we have different objectives. But I mentioned before, within the decision making for the climate change, because climate change is kind of deep uncertainties, we have to identify the most robustness solutions. The robustness, we have to identify the regretness, different type of the parameters to identify for this kind of robust decision making. So this is similar to the optimization, to the optimus solution. Maybe we have to identify the minimum value. For the robust decision, and also we have different like criterion to assess whether this is kind of solution is robust or not. I mean, for more detailed information, I think you can scan these QR codes. I think in this paper, in Dr. Yao Li, I mean, actually, she's my first PhD student. I mean, in the paper, I mean, she gave the more detailed explanation how to treat the epistemic uncertainty, also how to make sure that the decision making is more robust. I think you can find more information in the paper showing here. Or maybe you can send me email. I can send another paper that we are working on the robust decision making. Hopefully I answer your question.
Thank you. Thank you so much. Yes. Yes.
Thank you. Thank you.
Yeah. Thank you. Thank you, Abbas. Another question comes from Professor Daya Shankar. Daya, would you like to introduce yourself and your questions? Yes, your mic is on.
Hello.
Yes. Hello.
Are you able to hear me?
Yes, I can hear you. Good.
Okay. So nowadays the climate change is mostly artificial man-made. So how we can just increase the resilience of the people generally in the urban area? Due to the war scenarios, climate change increasing very rapidly because a lot of the smoke and war material are being thrown in the atmosphere.
Oh, okay.
And this is not a question, just this is a comment. So how people can just face this problem because this petroleum and other material also being shortage. So people are not able to become resilient in this present scenario.
Yeah. I think I will try my best to answer this question. I think in my perspective, I think the education is important. I mean, from academia, we develop this kind of fancy mathematical models, but I think the education to make sure that our language can share to the people. I mean, to the people who live like in the city. Like in Hong Kong, we work on the tropical cyclones. We try to have different type of education week. We invited like the people from high school, from other sister university. We explain these things in the layman language to explain what is the future climate change, have impact on coastal infrastructures. Maybe we have to like rely on some kind of animations, different things to show people if we do this, to that, do different things, what are the possible like the consequences. So based on this kind of small videos, smaller presentations, we can educate our people, like considering the climate change, what we should do. If we do not do right now, then we will maybe have the significant like consequences. I mean, the education is important. I think also it's like how to do the collaboration is also quite important. As mentioned for several times, our resilience is really quite a multidisciplinary or interdisciplinary approach. And also it's not only with academic area, but also with industry, within the government level. I mean, it means that all the stakeholders should work together, the industry, the professors, the government. Once we work together, we can make sure that the resilience development can really benefit the human beings who really use the city, who use the infrastructures. Again, the education importance, the communications, the collaborations is also really important to promote, to make sure that the urban people or even the rural area people know how to considering the climate change, like make the infrastructure adaptable to the future climate change. Daya, I really try my best to answer these questions. For others, maybe I not that familiar with the words and the materials. Maybe I cannot comment too much. I can only comment from the professor perspective, how we could educate our like societies, how we should collaborate with different stakeholders to promote the development for the resilient and sustainable coastal infrastructures.
Thank you for your response. Because we are the scientists and engineer, so we are developing some technology for the comfort of the people and trying to save their life and property. But our knowledge people take in and some other way. which is going to affect the bad effect on the society and our environment.
Yes.
So there is a need to convince our some utilizer of our knowledge, policymakers.
Yeah, yes. I think the communication is really important.
Communication, yes.
Yeah.
Thank you for a very nice presentation on climatic change and cyclonic effect. Okay, thank you.
Thank you, Daya.
Thank you very much, Yudong, for a very extremely comprehensive and all-encompassing presentations where you have very thoroughly described the whole process from reliability and let's say the degradation of structures to in fact sustainability, the inclusion of social vulnerability and everything else in the resilient cycles. I just wonder whether you can tell us a little bit more about how do you collect and curate the data for the different application that you have considered, because that clearly it's a very, where is the data coming from? Is the Hong Kong government giving you the information that you need? How else are you collecting it? How usually data has very different level of resolution, so how do you bring them together and so on?
Yeah, thank you. I think this is really good questions. When we're doing the research, I mean, we have doing the validation and the verifications. I mean, for the algorithm, we can doing the validation and the verifications using the benchmark examples. But now we are talking about the real world applications. We're talking about at the city level, how we could quantify the resiliency, how we could make our infrastructure ready to the future climate change. So here we are lucky. I mentioned for several times. I must thank the PolyU and also thank Hong Kong local governments. They give this kind of big research project. We work with my colleagues. For here, for instance, we work on these kinds of winds. We work with the Hong Kong Observatory. So it means that they have different type of stations. So based on this kind of station, we could do this kind of downscale validations, for the wind, for the flooding. So it means that we can, under given tropical cyclones, we could evaluate what is the wind speed at different locations, the wind profile, and also we could doing the validation for the flooding. And also because Hong Kong government giving this kind of real data for the validation for a hazard model. But that's only for the hazard model. And also we want to validate for our vulnerability model. Vulnerability model means that we want to identify the failure probability, the failure consequences for the coastal bridge, coastal buildings, because they can have different failure modes. So it means that I'll be doing this kind of site visit, and after the tropical cyclone, so based on this kind of field data, we can also do the validation for the vulnerability models. Once we have the validation for the hazard model and vulnerability models, we could quantify, we could evaluate the reliability and even the risk. But the tricky part is for the resiliency quantification, because for the resiliency quantification and modifications, validations, it's really tough to validate what is exactly the recovery time, because this is so many things involved within the resiliency quantifications. So right now we cannot do that kind of validation for the resiliency model. What we really try to do is that we have to consider all the possible factors could affect the resiliency. Then once we have this kind of real data, maybe we could identify the global sensitivity index, which parameters have large effects on our resiliency. So up till now, we have not done the validation for the resiliency part. And we do hope that we could form this kind of international, the group. Maybe I can share the data from Hong Kong. Dina, from your side, you can share some data from Europeans. I mean, then we could have this kind of collaboration. That's, I think, we can promote.
That would be very useful, yes.
Yeah, I think that's really useful. Data is really important for the resiliency research. I do look forward to the collaborations worldwide for this kind of research.
Yes, it's certainly needed, and I'm sure, yes, you are in contact also with the groups in the US and in Italy. Yes. Thank you very much again, and thank you for your answers. I think, do we have other questions? If you would like to ask any question, raise your hands, please, or open your mic. Otherwise, I think we will. Thanks everybody for participating, and thank you very much, Yudong, for delivering such an interesting webinar today. And sorry, Ali, have you wanted to ask something? Ali Osman, I see that you have. Hello? No. Okay. So thank you again very much. And we are getting into the Easter break here in the Western Hemisphere. So happy holiday to everybody, the ones that celebrate it, and see you soon towards the end of April. Thank you so much. And thank you, Zeishan, for organizing the webinar. Thank you again, Yudong.
Thank you, Tina.
Bye-bye.
Thank you. Bye-bye.
Bye.
See
Bye-bye.
you next month. Bye-bye.